about the proficiency quizzes, arithmetic quizzes. The first one is due a week from tomorrow. There are how many? 3. They are all open right now. If you want to go take all 3 in one sitting, you can. I don't recommend that necessarily, but if you have gone through and done the preparation, there's nothing wrong with that. You have 2 attempts before each deadline to be able to get those done and pass them with a 7 out of 10 or higher. So we need to be looking at moving that direction. Anyone who does not get them on the first 2 attempts, there is a backup plan for you, but the backup plan costs a little money. So we would hope that everybody prepares and goes and gets those taken care of. You will not be allowed to take both or 2 tries in the same day. So don't leave it till the very last day and then go try and get 2, because they'll only let you do 1. The idea behind that is, if you take it and you don't pass, you should do something about that before you try the next one. We've had students that run in and they've got an hour before the deadline. They go take it, didn't pass it. Walk out of the testing center, walk back in and take it. And well, duh, are you going to do any better? You need to go get some help. So that's why it needs to be at least a day apart. So anyway, let's talk the quiz. Does anybody have a question? Does anybody want to see one of the problems on the quiz? Are we okay? If you missed it, you know why. Be happy to do one or all of them, actually, if you need it.
Can you show us how you do that last one, the sum of the interior angles?
Maybe the last one for you, but it might be somebody else's number 2 or number 1. They're all in different orders. So, it's what was the question?
The sum of the interior angles of a decagon is 20 degrees.
The sum of the interior angles of a, what's a decagon?
10 sides.
Okay. So part of the quiz was if you got the vocabulary down. If you didn't know that, you have a real hard time with this, even if you know what to do. Who wants to try? Aubrey, you want to come and show us your approach to it?
Okay, so what I did for this one was I remembered our formula, which is n minus 2 times 380. That will give us the sum of the interior angles. And so if a decagon has 10, I knew that this would be 8. So I did 8 times 8 times 100. So I knew that this would be the sum. Does that make sense?
Yeah, I actually got that, but I thought that was wrong. So.
Did it mark it wrong for you?
No, I thought it was
Oh.
wrong, so I didn't do it.
Oh.
Yeah, I thought I would have got it wrong. Dang it. Okay.
So now you just got a boost of confidence today,
Yeah.
right?
Did it right.
All right. Did anybody attack this in a different way? Please.
Okay, so instead of doing the n minus 2, I just did the 10 times 180 first, which was, of course, I might butcher this, guys, was like this, right? Yes. And then minus 360 instead, because there's 10, so there's a decagon, so there's 10 sides, so you times that by 180. But we have to remember that the middle has the 360 degrees that we have to make sure we minus from all of these, so that gives us to the same answer as what she got. So that's how I did it instead.
Was that a different way? Yes. Did anybody do it a different way? Yeah, come on up.
So I originally did the 2 minus n times 180, but I wanted to check it, and so I went about it a really nerdy way. I know that 4 is 360, and I know for every 4 sides that I add, I'm adding 360. And so I just did 4, and sorry, it's for every 2 sides I add, I increase by 360, so then I get 6, go and 8, adds another 360, and then 10 adds another 360, and then you just add those up.
Does everybody knows what he means? He knows that a quadrilateral has 360?
360 degrees.
I think most 4th or 5th graders know that because what? A rectangle, right? Has 4 90-degree angles, and that's 360. And then he just said he knows that every time you add 2 more sides, it adds 360. Why does it add 360 for 2 more sides? Here's my quadrilateral. We'll do a rectangle. If I add 2 more sides onto this, so now I've got a 1, 2, 3, 4, 5, 6 sided, right? It added 2 more triangles, which is this 360. And then he put on 2 more sides, and it added 2 more 180s, which is 360. And that gave him this, and then he said, I'll go to 10 sides, I'll add 2 more. Does that make sense? Anybody do it a different way? How about this way? We know that if it's a 10-sided figure, that if it's a regular 10-sided figure, we don't know that it is, but the exterior angles, if I add all of them up, all 10 of them up, I get how much? 360. So if it's regular, how much would 1 be? Would be what?
36.
36, right? You can do that in your head. 360 total, 10 of them. That means this right here is 36, right? You with me? That means the interior angle of that is how big? 180 minus 36, which is what? 144. And if they're all the same, and there are how many of them? 10, I get 40. There's another way to do it. And so we have seen how many ways today? 4. And I'm betting there are more ways. And so if you ever get somewhere and you get stuck and you go, I can't remember this formula. I'll remember a formula. I wasn't sure Chelsea remembered a formula, but hers really came from a formula. What was her formula? 180n minus 3. She didn't state it. She just did it because she understood it. She didn't have to worry about memorizing a formula. She could see a picture of 10-sided with a point in the center, a segment drawn to each one of the vertices, creating 10 triangles. 10 triangles minus the 360 around the middle. You don't need them. If you understand something, memorization is not needed. Or it's not needed nearly as much. So not only should you try to make sense of everything you learn in math, you should try and help your students make sense of everything you learn in math. And then they don't have this short-term memory overload that everybody tries to. Well, math is all about formulas. If I know all the formulas, then I can do it well. No, math is about understanding and making sense. And if you can make sense, you don't need to memorize formulas. Okay? So I appreciated the way you took it. You didn't give me a formula, you just made sense of a formula that we had and got the right answer. Okay? And is it bad to memorize a formula? No. In fact, If you understand it, it's easy to memorize a formula. And if you forget it, what can you do? Draw a little picture and derive it, pull it back out, build it again, the same way we figured it out. Okay. Any more from the quiz? That we spent a lot of time on one problem, but that's an important thing I think in your teaching is that why else might you want to ask students their method? Get more than one approach.
Because sometimes you'll get a method that works for that particular case, but is not always correct.
Okay.
Like,
Right.
like when we had the first assignment where we were looking at making chords on the surface.
Ah. We led you down a path that turned out to not have patterns. Okay. Yes.
I think it's important to let students show their work, and that way they can teach the other students. That way maybe the kids aren't understanding the way you're doing it, but they can understand how the kid is doing it. And
Okay.
also, it reinforces it if they're teaching it.
So the student who, those that came up and did the presentation today actually got more out of this than those of you who are watching it, believe it or not. Okay? Do you have to know for certain how to do it before you raise your hand and come up? No, you could even say, well, I think this is the way. In the same way, how many returned missionaries in here? Not enough. In the same way that you're out on your mission, the rest of you may not be able to identify with this. You testify of something, and in the act of testifying, the Holy Ghost comes and witnesses it to you. You weren't real sure, but as you started, you got, yes, I know it's true. Go ahead and be a little bit brave if you're not quite sure of a method. Come up and share anyway. As you are sharing, guess what happens? The clarification that your mind, oh, now I am sure as I'm teaching. And so don't hesitate there. So yes, having the student come up gives the student an opportunity to teach. That student learns better. That's one reason to have students come up and share their methods. What else? Yeah.
If a student share their method, it can do two things. It can, if they're not getting the right answer, they may be interpreting the question wrong. So it can show you that the student understands how to do the problem, but they just might be reading it a different way.
Okay.
And then also, if they're doing it incorrectly with them writing it out and talking through it, they'll more times than not solve the issue that they're creating on their own.
Right. Now, had I been able to see what Anna was doing for her quiz, she said she got 1,440, but she just was, if I could have seen her approach, even if she'd made an arithmetic error, I could have said, oh, she knows how to find the sum of interior angles of polygons. You know what I'm saying? So having students come up gets you inside their head a little bit too, and it teaches kids that math is not just about answers, it's about thinking. And it's okay to think real well about certain things and make a little error, and you can help them get over that error. And okay, what else? Why else might you want to bring students up to the board?
Well, I was just thinking, I think the best tool for math is to have each kid to have a whiteboard, and so they have to write it out, and then when they're done, the students fold it up, and the teacher can see who's got it, who doesn't got it, the different ways they figured it out, and then they could select those students and be like, okay, I want you to share with the class how you got it.
But why do we want multiple solutions? That's a very good tool. So why do we want those?
Oh, I was just going to say along with that, even like these desks you can write on with Expo markers. And so then they're not putting it up, and if their answer's wrong, they don't get deterred. Their answer's right there in front of them, and only they, does that make sense?
The teacher who's walking by can see. All right, so that's a tool.
Well, it's just good to learn different ways, because each problem that you encounter, each situation is going to be a little bit different. So one method might be easier on this problem, but another method might be easier some other way. So just to have a more broad knowledge of different ways you could approach it, just improves your knowledge, I guess, of other areas as well, I guess.
All right.
And that's kind of like what I was going to say. Every child is different, and so one way might be easier for them to learn than another
The
way.
diversity, it helps for diversity. So there might be one of these ways and they go, oh, I didn't catch that at all. This end stuff really baffles me, this algebra stuff. But maybe one of these other methods will be helpful. Any other thoughts? I think the more ways that you can represent a problem, the more different methods you can use to solve, the deeper your understanding of that problem can be. Do teachers need deep understanding of the concepts? Yes. And with a deeper understanding, you can, so there's a number of reasons why we would look for it. I'll give you one more. You may have heard this expression where a math teacher said, do it this way. You know, it's my way or the highway. Well, maybe you've got a student that thinks really good in math, but they don't dare share it because their teacher says, this is the way to do it. And maybe the student's way is better than the teacher's. But that's the way the teacher learned it, and that's all he can do, right? So students get shut out. Students that could be invited into mathematics get shut out and blocked out because they don't get acknowledged. Their way of thinking does not get acknowledged. Does that make sense?
I feel like the best teachers are those who are continually learning, and they accept learning from other people, and they're open to it. I think those are the best kind of teachers because then they make their students feel comfortable to be able to make their opinion in class and say, well, I did it this way, and it's just beneficial for everyone.
But if your focus is on answers, as soon as Aubrey was done, I'd say, we're done. We're done. We're just, that's what we wanted. No. What we want is thinking. What we want is sense making. What we want is students that can reason. That's what we're trying to build. Because they need that in and out of math. Okay? They don't need the formula anywhere else but math. Well, we spent too much time on that, but that's important. And if nobody got any teaching ideas for their notebook today, they were asleep. That's all I can say. I need somebody to go to the board and share with us a Venn diagram using the alternate definition of trapezoid that we gave. The one that says the definition of a trapezoid is at least one pair of parallel sides. Anybody? Come on, you don't have to be certain. You can go up. Nobody's going to, jump down your throat. We may ask questions and we may... Okay, anybody? Everybody did this? Thank you. Let's get some room up here.
I can't remember if I corrected this to match the hickey or not, so I don't know.
Class can help.
Exactly right, but
I just thought of another reason why you ought to have students come up and share. Sometimes the teacher knows so much, they're using such high mathematical language that students don't understand it. Do you understand what I'm saying? The students come up and they present it in student language. And students go, oh, I have actually, student raised their hand, I don't understand this. I'll explain it. They go, I still don't understand it. Somebody who's sitting right next to them turned and explained it, and I'm going, isn't that what I just said? They go, oh, yeah, I get it. It has something to do with getting it from a peer that makes sense to them. And I think it's the language. It could be other things, but...
do we need to change anything from that?
I don't see parallelograms.
Oh, that's right.
So where would it fit?
Okay.
Stick it in
I
there.
need somebody.
Think on the fly.
Okay, I would do that.
Why did you put it outside instead of inside?
So on the second definition of a trapezoid, they could be two, they could have one or more pairs
Okay.
of, wait, so that needs to be the other way around?
I don't know, I'm asking.
So you're right, except for some, with that definition, some of those trapezoids aren't going to be a parallelogram. So basically,
Okay, so I need
just
to
take,
have, like,
part of it in, yeah.
Okay,
Here,
okay, so,
use this.
just, like,
Have it
So
cut
like
in
that.
partially through the isosceles trapezoids, because some of
Okay.
those can also be.
so like this?
Like cut into the isosceles trapezoids, because there are some isosceles trapezoids that aren't parallelograms, but
Okay.
then you would, it needs to include rhombus, square, and rectangle though.
Oh, okay.
Sorry, that's why it's just like cut in and then out.
Like this?
I,
Or? You do it.
sorry, cut in there and then
Oh,
go around.
okay. Okay.
Sorry.
So this is parallelogram. We've got a lot of.
Okay, go ahead and sit down, let's do some analysis here.
Good job.
Man, I can't tell what it is from here.
Quadrilateral is inside polygon, none of it's out. That means there aren't any four-sided figures that aren't polygons. Is that true? Okay. Question, comment?
I just have one question. Kites, where do those exactly fall? Because couldn't a kite technically, like, couldn't a square qualify as a kite?
Ben?
I actually had the same question because I actually found this cool little thing on a website called mathisfun.com. And it gives you the
It's gotta be good, right?
And it gives you a little program to work with where you can drag things around. And you can actually make a square with equal length, sides, and equal angles, and it'll accept that it's a kite. However, apparently one of the other definitions for it is, yes, it'll have two pairs of sides, but those pairs have to be different. The frustrating thing is, I also found another, it's not a Venn diagram, but it's a diagram of what fits into what. So like kites and trapezoids are all quadrilaterals. Parallelograms are all types of trapezoids, isosceles trapezoids. Anyways, it gets frustrating because it says a kite isn't a parallelogram, but that a kite can be a square. But shouldn't it be able to be a parallelogram?
If it's a square, it's a parallelogram, because every square is a parallelogram.
And if a square is also
So, what do we learn from this?
There's no Zach.
depends on what your definition is.
That anybody can build a web page and they don't have to know Jack. I don't know. You can't trust what you get on the internet, is what I'm trying to say. However, we have already acknowledged, and some of you said, I noticed that if you search on this, you find out that in England, a trapezoid isn't a trapezoid. They call it, what we call a trapezoid, they call a trapezium or whatever. So even with different countries that use the same language, you've got to... The thing we've got to be able to do is take a definition and then using that definition. If the definition is, for kite, is a quadrilateral with two pairs of adjacent congruent sides, and that's it, that could be a square. Right? Adjacent here, that one's congruent to that one, and this one's congruent to that one, but if they're both the same, it fits the definition, but if, however, the definition of a kite is two pairs of adjacent congruent sides, but the two can't be the same, then square doesn't work. Does that make sense? That's the one I've seen the most, that I think most textbooks would go with, which would not allow squares to be kites.
The one I had was two pairs of sides. Each pair of adjacent sides is equal length. The angles are equal where the pairs meet, and the diagonals bisect. At least one of the diagonals is bisected by the other.
Okay. And I think that fits the. So what are we going to use? What will you use? I think we'll use the one that says you've got a pair of adjacent sides that are, you've also got another pair of adjacent sides that are congruent, but that the two are not the same. Okay. And however you define them, that will determine what your Venn diagram looks like. This right here, kite, if we use this definition of they can be the same, this isn't the right diagram, right? But if we use the definition where the two pairs of adjacent sides that are congruent aren't the same as each other, then this is where it would go, out here. When you're doing this, let's see, this was the trapezoid circle, right? And this is the parallelogram. If she's got this outside here, that means there's a parallelogram that's not a trapezoid. Could that be the case with this definition of trapezoid? What was the definition? Trapezoid is a four-sided figure with at least one pair of parallel sides. So are there any parallelograms that don't fit that definition? Do you understand my question? Can you draw me a parallelogram that doesn't fit that definition of being a trapezoid, and that is having at least one pair of parallel sides? No. Therefore, this parallelogram, instead of coming out here, it's going to be around the trapezoid here, but then maybe come in and have some trapezoids that aren't, perhaps. And so this one would be the kind that looks like this, right? This one would be the kind that looks like those two legs are the same length. And those would be considered parallelograms, or excuse me, wouldn't be considered parallelograms, but there would be some isosceles trapezoids that could be. Okay? Does anybody want to ask a question about this? Yes.
In the key, it had isosceles trapezoid just around the square and the rectangle.
For this definition,
Right. And
it had come up and put your diagram.
Oh. I don't know the answer, so. I don't know if you guys can read this stuff. And then it was like.
I guess we need to define isosceles trapezoid. What's an isosceles trapezoid?
Trapezoid where the two sides that are parallel are equal.
That's one way we could define it. You could say it's this and this are the same. It turns out that the angles are the same for those that have the same length. And some people, in fact, that's the one I've used, is if the base angles are congruent, then it is a isosceles trapezoid. That's the definition most frequently given. It is a trapezoid where the base angles meaning they're not opposite angles, but they're the ones that, and it turns out that these are also base angles, okay? If they're congruent, then it's an isosceles trapezoid. So, the reason that isosceles trapezoid includes rectangles is because a rectangle has its base angles congruent. That's congruent to that, right? And that's congruent to that, and the same thing with a square. So it fits that definition. Okay?